Hey y'all, welcome back to our AP Chemistry flipped classroom. And today we're talking about composition. So this is composition of pure substances and composition of mixtures, but we're going to begin by discussing composition of pure substances. So we know the chemical formulas identify substances, and we're going to look at quantitative relationships between composition by mass or percent composition and empirical formulas, as well as molecular formulas. So just a few quick definitions to refresh our memories. Pure substance is any substance with a constant composition. So that can be either an element or a compound. And that can be an ionic compound or molecular compound. So when we're dealing with compounds, we can assume if it follows that law of definite proportions, remember that's one of our laws that help to establish the atomic theory, we can assume if it follows that law that those are the same compound. If compounds have the same elements in the same proportion, they are the same compounds. Following the law of definite proportion, we can find percent composition, which is the percent by mass of each element that makes up a compound. And this allows us, if we have two substances and we're trying to determine if they're the same thing, if we can determine their percent composition, then we can use that to tell us whether we have a pure compound or whether we have a mixture, whether those two compounds are the same. So our law of definite proportion says that we can calculate percent composition by dividing the mass of an element in a compound by the total molar mass of the substance. So as an example here, we have water. We have 2 atoms of hydrogen and 1 atom of oxygen. We know that the molecular weight of water is 18 grams per mole. And so we can take that 16 grams of oxygen divided by 18 grams per mole and get that it's 89% oxygen and 11% hydrogen. So we can go from a formula to a percent composition. If we're given percent composition of 2 samples, we can use that to determine whether or not that is a pure substance. So if we were to take a sample of water and break it down into hydrogen and oxygen and figure out what weight of hydrogen we had and what weight of oxygen we had, and it was not 11% hydrogen and 89% oxygen, then we would know that we didn't have pure water. So we can also take this information and apply it to empirical and molecular formulas. So in our compounds, empirical formula is the simplest whole number ratio of elements to one another. The molecular formula represents the actual formula for the substance. There are times when empirical formula and molecular formula are the same, but not always. So if we look at glucose as an example, the molecular formula of glucose is C6H12O6. We're all familiar with that one. Its empirical formula, reduced down to the smallest whole number ratios, is 1 to 2 to 1. So it would just be CH2O. Molecular formula is actual. Empirical formula is the simplest whole number ratio. It's called an empirical formula because we can determine it from empirical data or from lab data. So let's talk about how we do that. In the lab, we would be doing analysis and we would be getting masses of the different ones, and we can talk about how we do that. But let's just start with our procedure if we're given numbers. So if we're given the percentage of each element, we're going to assume, just to make the math easy, that we have a 100-gram sample. Then those percentages become grams. For each element, we're going to divide those grams by the molar mass of that element. Now it's just the element. Even if it's a diatomic element, it's just the mass of that element because we want to know how many moles of each element are present. We're going to divide each of those values by the smallest number, the lowest of those values. And if we're within 1/10 of a whole number, we can round to that whole number. If not, we have to multiply by a factor that gives me whole numbers for everything. And we have to multiply all of the numbers by that factor. And then the values that we've just found become the subscripts for each element. So let's take a look at a practice problem like this. So if we're asked to find the empirical formula of a compound, and it contains 69.94% iron and 60.0% oxygen. 30.06% oxygen, sorry. So first we're going to take the mass of iron that we're given, and we're going to divide it by the molar mass of iron. We're going to take the mass we're given of oxygen, and we're going to divide it by the molar mass of oxygen. And so for the iron, we get 1.252, and for the oxygen, we get 1.879. So our next step is to divide by the smaller of those two numbers. We're going to divide both numbers by the smaller of those two. So when we do that, we get 1 for iron and 1.5 for oxygen. This is where we reach that last step. We don't have whole numbers, they're not within a tenth. So we need to multiply both numbers by a factor that will give us whole numbers. And since it's a half, that's easy. We're just going to multiply both numbers by 2. And so this would give us an empirical formula of Fe2O3. So we're going to skip this practice one and do that in class. If we want to determine molecular formula, we need to know the molar mass of the substance. So we will have gotten that perhaps by mass spectrometry. We will have been given it in the problem. So first thing we're going to do is find the mass of the empirical formula. And then we're going to divide the molar mass by that empirical formula mass to find a factor. We're essentially figuring out how many empirical formulas are there in this molar mass. And then we're going to multiply all the subscripts in the empirical formula by that factor that we found in step 2. Okay, and again, we'll do this practice problem together in class as well as that one. So let's move on to composition of mixtures. So our chemical formulas identify substances by their unique combination of atoms. And because we know that compounds always contain the same proportion, that same percent composition, we can use that to identify whether we have a mixture or a pure substance, and perhaps what the contaminants might be in a mixture. So just a reminder, when 2 or more pure substances are combined, they form a mixture. Mixtures are not pure substances, so their composition can vary, but we can still determine percent by mass or mass composition of each substance in that mixture. And then we can use mole ratios to convert masses of products from the analysis to find the amounts of reactants that were in the original mixture. So we frequently use reactions in combination with percent composition to figure out exactly what was in our mixture. We can calculate a mass percent of any substance in the mixture. Same way we calculate any percent, part over whole times 100 gives us mass percentage. We frequently do elemental analysis on mixtures, and that allows us to determine composition usually quantitatively, but it can also be qualitative. It's a part of analytical chemistry. So this is very often how we get empirical formulas, that we do something called combustion analysis. So we basically burn it, and that means that we can figure out how much carbon dioxide, water, nitrogen oxide or nitrogen dioxide we have, and we can work backwards to get an empirical formula. We can use mass percent to determine purity of a substance or the identity of a contaminant. Okay, and we'll pick up with this problem in class. And as always, if you have any questions, let me know, and I look forward to seeing you in class.